Hello wonderful person, this is Anton, and in this video we're going to be going back in time and looking at one of the major mass extinctions on our own planet. And specifically we're going to actually discuss a study that may have discovered why back approximately 460 million years ago so many animals perished. Let's discuss this and welcome to What the Math. Over billions of years of existence of life on our planet, the life here experienced quite a lot of various events that you could call mass extinction. In other words, there were certain events where a lot of different species died out to be replaced by other species that would actually adapt to new conditions. Here's actually an interesting graph you can find on Wikipedia that shows you the percentage of various animals that died during various events throughout the history of Earth, specifically between about 0 years from now until about 542 million years ago. This one right here is probably the most famous one. This is when the dinosaurs died out, but you'll notice there are other really high peaks, specifically this one right here, where even more animals died. Now we're not entirely sure what happened there, but we might have figured out finally what may have happened during one of these events when quite a lot of different species died as well. One such event, Ordovician-Silurian extinction, lasted for roughly around 20 million years, and its origin is not entirely certain, but what we know about it is that it seems to have been caused by a very long-term glaciation of our planet, and essentially the temperatures here dropped, the levels of water also dropped, but the planet may have actually been covered by quite a lot of ice. Okay, maybe not as much as you see right here, but there was a lot of ice on the surface, and it may have lasted for millions of years. Although a slightly more realistic representation of the shape of the planet back then comes from this amazing simulation by Ian Webster, and the link for the simulation you can find it in the description below. And here, if you look around, this is kind of what Earth looked like. As you can see, there are a lot of oceans, not as many continents, and obviously there was a lot of life in the water, specifically near the shores of various continental shelves. And this life depended on being near the continent, but for some unknown reason, the water levels dropped, and we also believe that the temperatures decreased dramatically, cooling the entire planet. And by the way, this is also around the time when the first corals appeared, approximately 470 million years ago. And then, within about the next 20 million years, very large ice shelves started appearing on the planet. The entire planet suddenly experienced a very large decrease in temperature, and even to date, we're not entirely sure how it could have happened and why it lasted for so long. Until, of course, the recent paper that was just released a few days ago. And so this paper right here investigates in detail what they think and what they believe may have happened, and it does involve, as you can tell from the title of the video, an asteroid. And not just some asteroid, an extremely large asteroid that didn't actually collide with our planet, but instead collided with something else, or was somehow destroyed by some kind of an event that we can't really explain just yet. This extremely large asteroid, roughly around 100 or so miles across, or approximately 150 kilometers across, was somehow destroyed, and the entire mass of this asteroid basically escaped into the inner solar system. All of this mass that was inside the asteroid created so much various debris and so much dust in the inner solar system that, well, first of all, it actually probably dimmed our sun from a distance, giving it some unusual appearance and possibly even creating unusual dimming effects, similar to, of course, Tabby's star. But most importantly, as the Earth passed through all of this dust cloud, some of this, or actually a lot of it, started to fall onto the surface of the planet and basically accumulated in the atmosphere. Now, if it just happens for a day or even a year, it's not a big deal. But if it keeps happening for millions of years, which is what we believe happened, it eventually accumulates to the point where the atmospheric conditions change quite dramatically. In other words, pretty much all of the mass from this asteroid that you see right here compared to our planet, and it's actually relatively small when you think about it, all of this turned into dust and then eventually made its way into the atmosphere of our planet. Now, to give you a comparison, today we do receive a lot of dust from the outer space. Some of it is actually even interstellar dust, but overall The amount of dust we get every single year on the planet is actually right here. It's this tiny piece of rock you see. It's about 40,000 tons of material every single year. Now imagine that during this time, this amount increased by about 1,000 times. In other words, suddenly we started receiving this much dust. Now it might seem like it's not a lot, but 40 million tons of material in the atmosphere will definitely have an impact. And we think that it might have even been more than that. It might have been even 10 times more than what you see here, which is essentially something like this, which is sort of equivalent to receiving an asteroid that's about half a kilometer in radius or about 1 kilometer in diameter, and that's pretty much every single year. So this amount of material will eventually change the atmosphere, cooling it down, because suddenly you have all of this dust in the atmosphere, and all of this dust starts blocking the sunlight. And essentially, with time, the entire planet becomes cooler and cooler, and because it will take quite a long while for this dust to kind of disappear from the inner solar system or to get deposited on the surface of the planet, it will obviously take a long time for all of this to change the planet back to what it was like before. And so we actually believe today that it probably took anywhere from 10 to maybe even 30 million years for all of this to kind of finally stop. So for about 10 to 30 million years, our planet was not really warm. It was not really receiving enough sunlight because of this dust in the atmosphere. And all of this can actually be seen in the deposits, in the sediments from around that time. And this is exactly what the scientists behind this paper discovered. When they looked at the actual rocks, after looking at the specific layer that corresponded to roughly around 450 to maybe 430 million years ago, they discovered that removing all of the rock, you're left with only one material. Basically space dust, the type of material we usually detect around various asteroids, and more specifically objects like this. This is known as the L-chondrite meteorite. So that's what they discovered inside, and there was a lot of it. And it seems that this actually happened for a very long time. In other words, the only real explanation to what was happening here is that there was a sudden increase in meteorite dust coming onto the surface of our planet. And here is actually a picture of an actual smaller asteroid that was found inside of one of those sediments, approximately around the time when they think all of this happened. So this is a proof that many of the smaller meteorites were still kind of actively landing on our planet and may have contributed to this change of the atmosphere. And this photo I showed you was taken by the main investigator of this study, Birger Schmitz, and he also basically suggests that something may have destroyed this large asteroid, and it was probably another asteroid. In other words, the collision between two very large, very massive asteroids was very likely enough to create enough dust to essentially cover the entire solar system, or at least the inner part of the solar system, because we believe the collision may have happened between Mars and Jupiter. And it was thus kind of responsible for causing cooling effects that our planet Earth experienced, and was then responsible for causing the mass extinction as well. So in other words, it's not always the collision with asteroids that is responsible for causing the loss of various species on the planet, but it's also the collisions up there, above us. And this is actually a very interesting discovery because it does kind of put a lot of new things out there for us to study. At the same time, obviously, there were already scientists thinking, well, can we actually use this to somehow prevent global warming? And the answer to this is, yeah, no. Probably not. Mostly because anytime we try to create something like this on a very global scale, it actually backfires on us. So we have to be careful. We can't just collide two asteroids and expect that somehow the planet will start cooling. We'll probably cause even more harm than good. Oh, and by the way, one of the things I didn't actually mention is, well, why couldn't it be just another collision? Well, the reason for this is because there are actually no large craters around this time that would explain sudden changes in the atmospheric conditions. So even though there were some craters, none of them are big enough to explain the sudden cooling. However, this is a really good explanation because by creating enough dust in the inner solar system, there could definitely be a sudden change in the conditions of our planet, and it would actually be enough to make the changes very long term, lasting for millions of years, not just a sudden change like when the asteroid killed the dinosaurs. But when it comes to mass extinctions, it's not always asteroids and it's not always collisions like you see on the screen right here. Sometimes it's the actual life on the surface. We know that one of the mass extinctions was caused by the sudden increase in oxygen that was probably caused by oxygen-making bacteria, and that did kill a lot of things that couldn't tolerate oxygen. And today, well, there's humans. We are causing a huge change in the atmospheric conditions of the planet, and one of the studies I was investigating recently discovered that we're currently releasing more carbon dioxide than volcanoes, and when I say more, I mean like 100 times more. We are currently the most efficient releaser of CO2 into the atmosphere. As a matter of fact, we were able to release approximately 4 million years worth of fossil fuels into the atmosphere in the last 300 years. And that is pretty impressive. I guess not in a good way though. But anyway, we'll talk more about this in some of the future videos. For now, all you need to know is that, well, I guess mass extinctions are a little bit more complex than we previously thought. On that note, thank you for watching. Check out the study in the description below. Also take a look at Ian Webster's simulation that I showed you previously, because it's such a beautiful simulation and it's such an elegant way of teaching history. I'll see you tomorrow. Come back tomorrow to learn something else. Subscribe if you still haven't, and share this with someone who loves learning about space and sciences. And maybe even support this channel on Patreon, because it actually does help me quite a lot. I'll see you tomorrow. Space out, and as always, bye bye.